for the first part of our afternoon session. And our speaker is Thea Li. We'll be speaking on vibrational perspectives on determinization of finite-state automata.
Yeah, and I'm doing the literature like big box at the Oxford I didn't know what affiliations, but consequently, but that's it. It's where you can find me. Sorry. Oh, maybe right.
And speak up so that they can
hear
you online.
Stand up one
So, okay.
Yeah, you pointed that thing.
Don't need to punch here.
Sound kind of like
Sorry. I don't know what's
activate state.
It's not responding.
Okay, we move. If you need to point at that thing.
Okay. It turned itself off again. Maybe it's slowing down. Okay, yeah. I'll be here then. Yeah, so the purpose of this work was to try to construct a determinization for a categorical model of automata using universal constructions. So some of the objectives of the paper associated to this has been to carefully investigate the universal property of the determinization construction in terms of the relations between automata. And I present two different determinization constructions, one that generalizes an existing constructions to the model of automata presented by Colombo and Medias and Noam Zalberger. And then I also propose an alternative construction that is path relevant, but might be a little bit unorthodox, what a determinist automaton is. But this one, because it's path relevant, has a stronger universal property. So I assume that not everyone's familiar with automata, but the main idea is that you have a finite directed graph and you fix an alphabet. So the edges of this directed graph are labeled by letters in this alphabet, and we refer to them as transitions. And the vertices are referred to as names. So usually you would point out one state to be the initial state and a couple of states to be your final states. And so if you give a word to this automaton in your alphabet, then it tries to see if there is a transition over this word from the initial state to a final state, and if so, it accepts the input, and if not, it rejects it. So in this example automaton here, our alphabet is composed of the letters A, B. We have two states, 1 and 2, and this little arrow over there denotes the initial state, and ring denotes the final state. So it recognizes words like A, B, and so on. In this example automaton can also be seen as or we can encode this or model this using a functor from the free monoid over AB into the category of system relations by mapping the unique object to the set of states. In this case, just call them 1 and 2, so the set 1 and 2, and each morphism is mapped to the corresponding relation. So since there's a transition over A from 1 to 1, 1 is related to 1, and also 1 from 1 to 2, so 1 is also related to 2, and the A relation is same for B and everything else. So this view of functors from a free monoid into the category of system relations as non-deterministic automata was first presented by Thomas Bunge and Daniela Petersen in a paper from 2020, I think, and they also add some extra they add some extra structure to the domain category to denote the initial and the final states, but for the purpose of this talk and for what I've been doing, this is not very important. But this definition is very language oriented and models nicely logical aspects of automata. But since we're mapping into the category, or we're mapping into realm, it only interprets transitions as ways of relating states under a label. if we go back to this here, we see that there are two ways to do AB, like one looping over A and then going to over B, and the other one going from 1 to 2 over A and then looping over B. But since we're mapping into REL, this doesn't really recognize that. But for this model of automata, there exists a determinization construction. If we take our example automaton again, we can also see it as a functor, or we can model it as a functor over this free monoid, where the domain is then given by the free category over the underlying graph, with the functor denoting like a labeling functor. If you want to model automata as functors over a free monoid category, then you need to make sure that if you have a transition over a word, then this word can be split into like sub-transitions over each letters. And for this, we can impose the condition on the functor to be ULF or have the unique lifting of factorization property. And this U of automata was presented by Milius and Seilberger. They also add some data to denote like the initial state and the final states, but for the purpose of this talk, this is not very important. By a relatively classical result, we can see a UF functor into a category C as a pseudo functor from C into span set. And this pseudo functor then maps each object to its set fiber and each morphism also to its set fiber with source and target projections. So consequently, we can see ULF automata over, I have this B sigma is just like the free monoid over alphabet sigma. These correspond to pseudo functors from B sigma into span set. If you want to impose the finiteness condition, you can also impose the condition of factoring and then. So we see here that REL is a subcategory of span set. Consequently, the notion of ULF automata subsumes the notion of REL automata. And if we look at our nice running, it will be a running example. So our nice example here, then the span set approach actually recognizes that there are two ways to do the transition AB. But I said that we were going to be talking about determinization. So consequently, we also need like a model of deterministic automata. The difference between a deterministic automaton and a non-deterministic one is that for the complete deterministic automata, if we pick a state and a word, then from this state, we have a unique way to do a transition from this state over this word. And just if you look at this from a factorial perspective, this is exactly the property of being a discrete off vibration. And by the Gaussian deconstruction, any discrete off vibration corresponds to a functor into set. We also, since we're talking about determinization, we need like language preservation. We need a way to relate automata to each other or say that they're similar stuff. So we borrow some notions from label transition systems. So if we have two label transition systems, which essentially automata are, then we say that a relation on the set of states of these is a simulation if we have a transition over a word W from Q to Q prime in L1 and a state S that relates to Q using this relation. If there exists an S prime, so that a S and S has a transition over W to S prime, and S prime relates to Q prime, then this is a simulation, or L2 simulates L1. And we can also do it the other way around. If we can do it the other way around, it's referred to as a bisimulation. Consequently, we can define a type of simulation, or we could say that a simulation from an automaton or a span set automaton F to F prime is a lax natural transformation between these two functors. And the explanation for this, or to explain this, we can look at the lax naturality square for this transition for a given for W. So if you look at, we have a pair Q Q prime and S with a lift in the span that's given by this side of the diagram, then we necessarily have a state Q and the automaton F such that there is a transition over W from Q to Q prime. And also there is a lift of the pair S and S prime, or S and Q in the span alpha. And since we have this two morphism here, we also get an state S prime and F prime, such that there is a transition from S to S prime over W, and there is a lift of the pair S prime, Q prime, and alpha. So if we impose other conditions on this automaton, we can also get different types of simulations. So if this natural transformation instead is pseudo, we also have the probability of we can look at other side of the span and get this data. And since this is pseudo, we also get a Q and F such that there is a transition over W from Q to Q prime, and SQ prime has a lift in alpha. So span set is on the one morphism side a dagger, or has a dagger structure. So if we're given a lax natural transformation whose daggered version also is a lax natural transformation, then this constitutes in a bi-simulation, because if you look at this side of the square, then you're given this data and you can fill it out because, well, this is just the lax naturality of alpha dagger. So I mentioned before that REL automata has a determinization procedure. And if you think about it, determinizing a REL automaton is just turning a functor into REL, into a functor into set. So what Kokumbe and Peterson do is by post-composing by a functor from REL into set. So there's a natural choice for this, since REL is a Kleiter category of the power set monadal set. This also gives us a canonical simulation of REL automata by its determinization, is given by the co-unit. We also get a unique factorization of simulations from a deterministic automaton to a non-deterministic automaton via the canonical simulation, which is essentially what this equality of natural transformation does. So I said we wanted to emulate this, and but it turns out to be quite non-trivial because span set is a bi-category, or automata, or pseudo functors. So it's not easy to map back into set, but it turns out that there is a local adjunction between span set and REL. So a local adjunction between two bi-categories is comprised of two functors, one in each direction, that induces a family of adjunctions of this form between the home categories. And these family of adjunctions are natural in B. So the local adjunction between span set and REL is induced by the inclusion of REL into span set, and the kind of forgetful image functor of span set into REL, which is given by like its identity on objects, and then each span gives a, if you look at the span as something like this instead. Given by, these are the two legs that we mapped from the image. And this will be a relation of the codomain of the both on both domains. So this gives us a relation, and what it does on the two morphisms just follows by doing this definition.
Sorry.
Yeah.
I is a lax functor or
Which one? This one?
yeah, the one.
Yeah, it's a functor between bi-categories. So it needs something, but it's just inclusion.
It's not because of composition.
No, it's a lax functor that way, of course. So to determinize a span set automaton, we can just post-compose by this image functor and then do the REL automaton determinization procedure, and we get here a canonical simulation by pasting the co-unit of this adjunction, and we're given a lax natural transformation by the local adjunction with the like 2 arrow given by the eta of the local adjunction. And it turns out that we can define like one-sided inverses at least for each of these two. So each morphism or like each simulation of automata that looks like this also has this nice factorization property. But so what does this determinization actually do on like the automata level? So if we look at our nice running example, it maps the set of states to the power set of the set of states, and each letter, since it factors through rel, we map it to the corresponding relation. There's a lack of space, so I just denoted it by delta A. And this is mapped to a function from the power set to the power set that maps each subset to the set of all things that are A related to anything in S. So if you know a little bit about automata theory, then you might recognize this, or you might see that this resembles the classical determinization procedure. And indeed, and when we're taking free monoid as our base category, then this actually recovers the classical determinization algorithm. But to see this more clearly, you can also just turn our set automaton into using the growth ending construction into like the Fibrational approach and look at what morphisms look like in the domain, which is the category of relations. So I started this talk by saying that mapping into rel kind of identifies paths, and this is not always something that you would want. So we could also imagine like a path relevant determinization procedure by using multisets instead of subsets. Sorry, how long do I have?
About 9 minutes.
Okay, yeah, then I have time. So something
And ask questions too.
yeah, okay. Yeah, okay. One key observation here is that a span like this of finite sets always gives a function of this form. So this is important for later on. But we can define a multiset relative monad from fin to set by this map. And consequently, if we're looking at only span fin, or like automata that whose codomain are like the span of finite sets, then we can define like a multiset determinization that factors through the relative Plicy category of the multiset relative monad instead of rel. And we also get this nice canonical simulation, but this time we have pseudo natural transformations instead of lax natural transformations. So this gives a stronger like canonical simulation. And to define this pseudo natural transformation, we needed this observation that each morphism of this form is kind of a span up to your choice of apex. And again, we can again define like a one-sided inverse for each of these pseudo-natural transformations. So again, we get this nice factorization property. So some conclusions and takeaways is that, we actually succeeded to express determinization as a universal construction. So that's very nice. And we can, something that is also quite interesting is that we can recover the determinization algorithm via such a construction using the power set monad. And if we would like to have a notion of path relevance, we can determinize using like a multi-set relative set. Thanks for listening.
Questions, comments?
Is the multi-set and the path relevance like
counting how many ways there are to get from one state to the other? Is that,
It's, yeah, it
Or-
almost does that, but it like recommend. Yeah, you can say
it's
that.
all the ways and like a multiplicity?
Yeah.
Thanks.
Firstly, thanks for the talk, it was very interesting. I thought that the growth and deconstruction played a role as well with the vibration perspective. So I was wondering whether you could apply that to, I mean, you were looking at things like pseudofunctors into startup set and maps into REL as well. You can apply growth and deconstruction to them and get things like conjugate vibrations over your base and stuff like that. So I was wondering if you could push that even further and get a completely vibration based view on this.
You mean like what automata that are based on the shape functors in the type? So there was this idea that Converse vibrations also would encapsulate like epsilon transitions, that are like, transitions that don't have a label, since we can using Converse functors map some morphism to identity. But I don't know whether this was explored further.
Yes, so the way you construct something from REL to set is by viewing REL as a classic kind of positive.
Yeah.
So that kind of makes me think of replacing that with some other monads, like if you have automata that are maybe stochastic or something. Would this sort of idea also work for that?
Yeah, of course, because you have the adjunction. Basically, this is just the property of junctions between like base. You have functor, if you have an adjunction between like a codomain up to like functor categories, an adjunction between two endofunctor functor categories. Like function pushing the adjunction. Further questions?
Really enjoyed this. I was wondering about in the vibrational perspective with the ULL functors, where do the lax natural transfer, where do the simulations appear in that? Or do they?
If you want to like transform simulations into the last approach, then you can consider like spans of the last functors with some type of vibrational property on the legs. But it's a little bit more noisy work, but that's just not digital transformations.
That's here again.